Hello everyone, welcome to In 5 Minutes. In this video clip, we will discuss another type of special filter which is called comb filter. We have discussed a notch filter before this. The definition of notch filter says that there will be one or multiple notches or perfect nulls in the frequency response characteristic. Now, comb filter is something similar to the notch filter. It can be viewed as a notch filter in which the nulls will occur periodically across the frequency band. That's the only difference. So comb filter will also have perfect nulls occurring in the frequency response. Just that in notch filter there may not be any relationship between those frequencies at which the nulls are occurring. In comb filter, compulsorily those frequencies must occur in such a way that the notches or the perfect nulls are occurring periodically. So there has to be a proper pattern followed in terms of frequencies at which the notches are occurring. So a comb filter is again a filter in which you will see multiple perfect nulls or frequencies where magnitude drops down to zero, but this notches must occur periodically, and hence there is an analogy to an ordinary comb, and hence we call it a comb filter. Comb filters find applications in a wide range of practical systems, such as in the rejection of power line frequencies again and their harmonics, in the separation of solar and lunar components from ionospheric measurements of electron concentration. So whenever we carry out such type of measurements, there are often solar and lunar components which introduce some unwanted frequencies as well as their harmonics. To remove that, we use comb filters. Also, in the separation of clutter from fixed objects in moving target indicator radars. So in radar also comb filters find their applications. In short, one very important type of digital filter. We will first consider one standard filter function and we will prove it to be a comb filter, and we will also draw its frequency spectrum at the end. So we will discuss a comb filter in its one very simple form. So I'm saying that consider a moving average filter. Now what is a moving average filter? Moving average filter has output y of n equal to 1 upon m plus 1 into summation x of n minus k, where k will vary from 0 to capital M. Now this is called moving average filter for a simple reason that if I quickly expand the right hand side, although we will not use the expanded expression, but if I expand this, for k equal to 0 I get x of n. If I put k equal to 1 I get x of n minus 1. If I put k equal to 2 I will get x of n minus 2, and so on. Last I will have x of n minus m. So you can see that this filter basically, what does it do? It simply adds the current input sample. X of n is the current input sample with its past m number of input samples. So these are nothing but past m input samples. So it adds the current input sample with m. Why m number of past input samples? Because it starts from 1, x of n minus 1, x of n minus 2. It will go up to x of n minus m. So total it adds m plus 1 input samples, and it divides the sum by m plus 1. Now this is nothing but the average operation. So it is called average filter. It is called moving average filter. That is simply because every time I take the next value of n, I will consider next value of input sample and new past m input samples. So every time that window over which the average is being taken will keep on shifting towards right by 1. So that's called moving average filter. By choosing the value of capital M, I can decide how many input samples I want to add and take the average. Let us do a small analysis of moving average filter. Now you might be wondering how come suddenly we are talking about moving average filter, whereas the topic is about comb filter. That is because moving average filter is nothing but a comb filter in its nature. So we will prove at the end of the analysis that moving average filter comes out to be a comb filter, and hence it also becomes one standard implementation of a comb filter.